So let's talk about compound interest and how it's different from simple interest. Okay, so I'm going to do a similar example that I did with the simple interest video to show you how they differ. So let's say that you start with $300. Okay, so you're now going to grow this $300 just like we did in the simple interest example. Over 1 year, you get, let's say, 10% interest, just to make the math easy. Okay, so the interest in the first year is going to look the same. You take 10% of whatever your investment was. In this case, 10% of 300 is 30. And then you add that on top. But the difference is, instead of adding on top and then leaving your principal the same, your whole principal changes. Okay, so your whole principal is now 330. Okay, and then the next year, when you take, 1 year, 10%, you take 10% of this principal, which is going to be a little bit bigger. In this case, it's going to be $33. Okay, and then your new principal is going to be bigger. It's going to be 330 plus 33 is $363. And so on, and you're just going to keep going up like that, right? You're taking 10% of this principal and continuing to go up. So the big difference is that as you increase your earnings, as you increase with time, the amount you increase your principal by also increases. Right, so this last example here, 363, 10% is 36.3. So in our fourth year here, we now have, these might not be to scale, but this would be 399.30. Okay. So it's just a little bit more than in the simple interest video. In this case, I think it's $9.30 more-ish. So it's not much more, but it can grow a lot over time, and you can see that value increase exponentially over time. Okay, so we're going to look at a couple different formulas to use with compound interest, some problems using compound interest, and then just some practice to get it down. So let's start just by looking at the formula, since it has a little bit of a breakdown for us here. So first, it is the future value equals the present value. Much the same right now, times 1 plus, yep, still pretty much the same. Then we have r over n. Okay, well now that's a little bit different, and that's to the power of nt. So now we've got some exponentials in here, right? Like I said, compound interest is exponential growth. This is why. Okay, so let's outline what each of these is. So first off, we have FV, which is our future value, right? So that's the value at the end of the investment. PV, which is our present value, or our principal. And that's what you start with. Then we have R, which is our rate as a decimal. And N, which is new, which is our compounding periods. I'll talk about that in a moment. And finally, T for our term. It's again just how many times generally it's how many years in compound interest. Okay, so compounding periods I want to talk about a little bit. So if you've ever seen an investment that is set up to be, annually, or maybe you've seen semi-annually, or even quarterly, right? These are compounding periods. Okay, so it's how many times per year something is going to compound, how many times we're going to redo this calculation where you increase the amount of interest that you're earning. So it's when you get the interest and then recalculate. So we also have, so annually, semi-annually, quarterly, monthly is another common one. Weekly, uncommon, but still a thing. Daily even. Usually that only is for credit card debt. But still, we should know what all these mean, because these are all values for n. So in these cases, we have different values for n. So annually is just once per year, so n is 1. Semi-annually is twice per year, so n is 2. Quarterly, 4 times a year, 4. Weekly, 12 months in a, pardon me, monthly, 12 months in a month. 12 months in a year. There we go. So n is 12. Weekly, there are 52 weeks in a year, and daily, 365 days in a year. Okay? So our compounding periods will be part of our formula in 2 places. I should probably draw an arrow there. Okay? So let's take a look at an example so that we can practice. So let's take a look at this one here. $520 invested for 8 years at 4.5% compounded monthly. So let's set up our equation. So the future value is what we're trying to find today, equals our present value times 1 plus r over n to the power of nt. Now we can start filling things in. Future value we don't know, present value we do, $520. Times 1 plus r as a decimal, 0.045. Remember that's just our 4.5% divided by 100 gives us 0.045. Practice makes that kind of automatic in your head, but if you need to write it out. Over n. Now n, compounding periods. It says compounded monthly. So looking at our table here, or even just thinking how many months in a year, we get 12. So divided by 12 to the power of 12, since it was n, times the number of years, 8. Okay? So we take this step by step, because with exponentials, we want to make sure that we do everything in the right order. So multiplication and division comes first in our bad math, so we do that first. So future value equals 520. I know this is multiplication, but brackets come first too, so we do everything in the brackets first. So we're going to take our 0.45, or rather 0.045, divided by 12. That gives us 0.00375, but we're going to just add the 1 real quick, so we get 1.00375. Usually this will be a small decimal, so adding 1 is a very simple step to take there. And that's to the power of 12 times 8. So 12 times 8 gives us 96. Okay. Now, bad math, we've done the brackets, so let's do the exponents. So future value equals 520 times, and we're going to take our big number here, our 1.00375, and then we're going to take that to the power of 96. Now, it sounds like it's going to be a huge number, but because it's a decimal, it doesn't really get much bigger. We get 1.43236. Now, I include a lot of decimal places here. If you're using a calculator, it's best just to keep every decimal place you possibly can. I'm just using a few here since I'm writing it down. But if you come up with an answer that's maybe slightly different than an answer key, that's probably why, is that it's just a little bit off there. We've rounded differently, that's all. Okay, but last step, we multiply the 520 by our factor here. So if we multiply that by 520, we will get, $744.83 if we round it. Okay, so that's our final value there. Okay, so compound interest, it looks complicated. I get it. As soon as we see exponents, we start thinking, oh, that's going to be difficult. But if you take it step by step, it's not much harder than simple interest, right? There's a little bit of, errors happen around these 2 steps here. But you can get to the end simply by taking it step by step in simple, small steps. So let's look at one more thing here. We're going to look at the rule of 72. Okay, this rule is amazing. Okay, so here's how it works. So let's say that you invested, I don't know, $10,000. And you wanted to know, well, how long will it take to double my investment if I invested at, say, 3% interest? How many years will it take at 3% interest to get to $20,000? we could do a bunch of math where we take, this is the present value, this is the future value. Let's solve using this as the rate, and we're going to solve for term and compound interest. That's difficult to do by hand. Or take the rule of 72, which is the years to double equals 72 divided by the annual rate of return. Seems a little simpler, I feel. Okay, so let's estimate this example. So you want to get from 10,000 to 20,000. It turns out these numbers don't matter. They just have to be double for this to work. Okay, so we just take years to double. So years to double equals 72 divided by our annual rate of return, which is 3%. And in this case, we actually use the full 3%. We don't go decimal. This is one of the only times we don't. And that equals 72 divided by 3. So we take 72 divided by 3 equals 24. Ta-da! How simple is that? It will take 24 years to double at that percent. Now, it's not perfect. It's not like this is going to be the exact time it's going to take, but it's a really good estimate. Okay, so rule of 72 is a great estimation tool. It is not a perfect estimation tool. Okay, calculating everything out is always going to be better, but this is faster. And until we go over some techniques that we'll go over in a new video, this is about as good as we can get for calculating that. Okay, so that's going through compound interest, the difference between compound and simple interest, and the rule of 72.